This is Mrs. Palmer-Quay with the second video for Module 11. In this video I want to talk to you about solubility. When we're talking about solubility with solutes and solvents, when a solute can dissolve in a solvent, we say it's soluble. And if it can't dissolve, then it is insoluble. These terms are used for solids, liquids, and gases as they dissolve into each other. But if we're talking about two liquids and if they will dissolve in each other or not, we can also use the words miscible or immiscible. So miscible liquids are two liquids that will dissolve in each other, and two immiscible liquids are things like water and vegetable oil, which will not dissolve into each other. The amount that something will dissolve, the amount that it is soluble, is known as its solubility. And the level of solubility can vary. Logically, one substance can be more soluble than another, but even for any particular substance, a change in the temperature can change its solubility, and if you're talking about gases, the change in pressure can affect the solubility. Solubility, the amount of solubility or the level of solubility, is typically expressed as a grams per 100 grams of your solvent. And in water, of course, that would be per 100 milliliters could be used instead of 100 grams, since water's density is 1 gram per milliliter. We have a solubility curve, or many solubility curves on this graph on the page here. And I just wanted to show you that solubility curves have many different shapes. Sodium chloride has a fairly level solubility curve. There's not much slope to that line, which means as you increase temperature, you really can't dissolve a whole lot more salt in your 100 grams of water. But something like potassium nitrate or calcium chloride, their solubility curves do show a great increase in the amount of solute that you can dissolve in water as temperature increases. Cerium sulfate actually has reverse solubility. You can see that you dissolve less as the temperature goes up. So there are a few exceptions to the rule here in chemistry. The words we use to talk about how much solute is dissolved in a solvent are saturated or unsaturated. A saturated solution contains the maximum amount of solute that can be dissolved, whereas an unsaturated solution contains an amount that is less than the maximum. Most of the time we're working with unsaturated solutions. We are not concerned with having the most solute possible into our solvent. We just need enough of that solute present to undergo whatever reaction we are doing. If you look at the solubility curve, take note that any space to the right of the curve of any line, that will be where you can find an unsaturated solution. So if you take our calcium chloride here as an example, and 20 degrees being room temperature, if we mixed 70 grams of calcium chloride in our 100 milliliters of water, we will have created an unsaturated solution because this spot for 70 grams is to the right. It is below the curve. Here's our curve for calcium chloride. At 20 degrees Celsius, we could mix in probably about 76 or 77 grams of calcium chloride, and that would create our saturated solution. That's the maximum that we could mix in. But if we took our solution that contained our 70 grams of calcium chloride and we cooled it down, we took it down in temperature to 15 degrees instead of 20 degrees, then we would be on the line and we would have created a saturated solution by decreasing the temperature. So these terms saturated and unsaturated are not firm. They depend very much on the temperature of the solution because the amount of solute that can go into solution is temperature dependent. Here's another example with our sodium chloride. At 20 degrees Celsius at room temperature, the amount of sodium chloride that can dissolve in 100 grams of water is 36 grams. So if you try to dissolve, or if you successfully dissolved 30 grams of sodium chloride in your 100 milliliters of water, you've created an unsaturated solution because you could still get 6 more grams in there. But if you tried to dissolve 40 grams in, you would end up with a little pile of sodium chloride, even though it looks like sand here, a little pile of sodium chloride on the bottom of the beaker. You created a saturated solution in the beaker, but there were 4 grams that you cannot dissolve because there's no more space for any more solute to be dissolved in that solvent. The solution is saturated. If you heated up this beaker, though, you might be able to dissolve those 4 more grams in. Though remember, the curve for sodium chloride was pretty flat. There's also something called a supersaturated solution that contains more than the maximum amount of solute that can be dissolved at a given temperature. And these are created by making a saturated solution at a higher temperature and allow it to cool undisturbed. These situations or these solutions are sort of ripe for making crystals. And then you can have recrystallization coming very rapidly if you add a seed crystal. So growing crystals at home, you often work with a supersaturated solution and then you add a seed crystal. So this illustration at the bottom is sodium acetate, and we have a seed crystal being added into the supersaturated solution in the first picture. And you can see these crystals growing very rapidly and filling up the beaker as that supersaturated solution turns back into a saturated solution with a whole lot of crystals. So whatever amount of liquid that's left here on the top of this third beaker is going to be a saturated solution. All the extra material, the extra solute, has crystallized out, but it won't crystallize past the saturated part. It won't make it an unsaturated solution. It will just go to the saturation point and then stop. As I mentioned earlier, solubility generally increases with temperature, except for a few selected compounds, and this pertains to both solids and liquids. But solubility decreases with temperature when it comes to gases. So gases are different than liquids and solids. Solubility of a gas also in a liquid increases with pressure. Pressure really doesn't have any effect on solids or liquids. This illustration might help you visualize what happens when you increase pressure in a situation where gas is dissolved in liquid. The gas is actually existing in equilibrium with the gas in the atmosphere above the liquid and that gas dissolved in the liquid. Some particles are moving out and others are moving back in, but at equilibrium the rate is the same, and so nothing really changes. However, if you increase the pressure, you're in a sense concentrating, putting in more gas particles above the liquid than in the liquid, and so it changes the equilibrium so that you end up with a higher concentration of gas dissolved in the liquid. And the reverse form, if you decrease the pressure, you will then decrease the concentration of the gas dissolved in the liquid, which is something I think you can visualize by thinking about your experiences with carbonated beverages. When the lid is on, you've got the equilibrium existing between the surface of your carbonated drink and the tiny bit of atmosphere that's there in the bottle. But once you take off the top and allow the contents of the drink to be exposed to the general atmosphere, then carbon dioxide wants to leave, and you hear that, hissing sound when you take the top off. In fact, if you leave it out for a long period of time, all of the carbon dioxide will eventually leave. And if you let this bottle warm up, increase the temperature, you also encourage more of the carbon dioxide to leave. So in the rules about gases, that increasing temperature and decreasing pressure will cause a gas to come out of a liquid solution to not be as soluble. If you just think about your experiences with flat soda, you might be able to keep those straight. And this finishes my discussion on solubility.